Okay, so let's do this first problem here. Show that the following matrix is diagonalizable, and then we can try to find m to the n, okay? Now, but let's use algebraic manipulation program to do this and see if we can do it. So this procedure is so that basically what you want to do with this is you can go through and do all the calculations with WX Maximal or another program, and that will speed things up. So here's our matrix M, and then because here the thing is the procedure you want to follow to see that it all works. Okay, so this is 1, 1, 1, 1, 1. Okay, so we have M. Now, what do we need to do? We need to find the eigenvalues and the eigenvectors, right? So after we've entered the matrix using enter matrix here, we can then just directly find the eigenvectors. Now, if you remember, this form here says that the eigenvectors are here, so repeated. It looks like it's repeated because you can see the eigenvectors here are 0 and 2, but the 0 occurs with multiplicity 2. Okay, but there are 3 eigenvectors, right? So what we can do is then we can let's form D. What we can do is we can enter another matrix, and this is going to be another 3, but this will be a diagonal matrix, D, and if we instead of general, we change diagonal, it will fill in all of our forms. This is going to be 0, 0, 2. Okay, so there's our diagonal matrix. Sort of simple, right? But now we need P, okay? So P is going to be, we can enter that. This will be P, and it'll be a general matrix, okay? So it's going to be these columns. So I'll have 1, 0, minus 1, 0, 1, minus 1, and 1, 1, 0. Okay, so there's P, and you can check that 1, 0, minus 1, that you've done it correctly. And then we need its inverse, so we can go and do invert matrix. And then we can name this as, say, inverse, or we can say it P inverse colon, because that will name it and press enter again. Oh, then it's the wrong one. So we have to do P inverse is the inverse of P. And we've got that. And we can check this right away. Let's do P dot, P inverse. Right? There's the identity. Okay. Are you guys following along with this? You can do this too. So yeah. Okay. So now we have P and P inverse, right? And we have D. So we want to see that we want to look at this form here and say, well, M to the N equals P D P inverse. Right? Because let's see if we did this correctly. Yeah, because we haven't done any of that yet. We want to see that the original matrix M here should be P times D times P inverse if this is all to work out. So we can check that. We can do P. Let me make this on top. P dot D dot P inverse. And, there you are, M. So it worked. Now, we can try, let's see, I don't know if I can do this with an arbitrary That's the only issue. The question is, we know that we can do it easily. Here, D to the N, this is going to be D to the nth power, is going to be, let's do it, we can enter it. 3 by 3, this will be D to the nth power. And it's going to be a diagonal matrix. And 0 to the n is going to be 0 to the n. This one's going to be 2 to the n. Okay, there you have it. So this is the nth power. So then we want P dot D nth P inverse. And there you have what should be, we can label this as M to the nth power. And you can see this, it's actually pretty simple because it's like 2 to the n minus 1 times the original matrix, right? So it's just getting large, it's just getting scaled up by a common factor. And you could try this out. Like, for example, if n is 1, you get the original matrix back. But if n is 2, you should get 2, 2, 2, 2, 2, 2. Then you could check it. You could do what is m dot m. Well, there it is. 2, 2, there's the 2. So you can check your general formula with this. Okay, so this makes this procedure doable to where because we want to use this, we want to use eigenvectors and eigenvalues, this procedure to investigate some models rather than being, just whenever you can find them, you understand what they are and how it works. For simple cases, you can do it by hand, but this way you can use the automation to understand what's going on and check that you have the right answer so that everything works. Okay. And then you can see that you shouldn't be afraid of doing one of these examples. And I think some of the regex exercises actually ask you to do some examples with algebraic ones. Oh, there's one other nice thing we haven't. This is sort of a kind of this next section is an aside, but the trace of a matrix. Let's do the trace of a matrix like let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. The trace of a matrix is the sum of the diagonal entries, right? The trace is just the sum of the diagonal entries. Well, so this is just going to equal 1 plus 5 plus 9, right? Well, here's the nice thing. The trace of a matrix A equals the trace of the matrix P, B, P inverse. So let's say A and B were similar matrices, right? Well, it turns out that the, how do you say? There's some, you can show that there's some theorems, like the trace of a sum of matrices is the trace of a sum, and the trace of AB is equal to the trace of BA. Okay, well, let's see what this last property means for similar matrices. This means this is equal to the trace of, I can take one, this is one matrix, this is the other, this is the trace of B, P inverse times P, which then the P and the P inverse go away. Let me make this a little clear. I've got B and P inverse, so I've done this there. I've inverted that one to put the P on the other side, and the P inverse, this is just going to equal the trace of B. So this property of traces, that the trace of a product, doesn't matter which way you go, enables you to say that similar matrices have the same trace. Okay, well, that means that the trace of M equals the trace of P D P inverse, which equals the trace of a diagonal form. The trace of diagonal form is just the sum of the eigenvalues. So the trace of them, so that means that like for this matrix here, we can just say 1 plus 5 plus 9 equals 15. So we know that the eigenvalues for this matrix add to 15. These aren't the eigenvalues. We just know that lambda 1 plus lambda 2 plus lambda 3 equal 15. Now, the square matrix, that would be pretty good because you move a 2 by 2 matrix, okay? Now, and then so that's why traces are useful because you get some information about the eigenvalues. Now, it turns out, let's look at the determinant of a product of matrices also equals the determinant of A times the determinant of B, right? Which equals the determinant of B times A, because I can switch this and then do it backwards, right? So if I take the product, so I can do the same thing, and then I can say, well, the determinant of M equals the determinant of the diagonal form, right? Because I can put for M here, I put in P, dP. Then this property is the same with the trace has, so I can put the P over and do this. But this is just the determinant of the D is just the product of the diagonal entry. So it's just the product of the eigenvalues, right? If it's a 3 by 3 matrix. So therefore, you have two equations right away. If you know the determinant of the matrix and you know the trace, you can right away have two equations for its eigenvalues, which is probably why in the textbook they have various problems where they give you one of the eigenvalues. So if you have two of these equations and you have the third eigenvalue, you can like if I knew that one of the eigenvalues was -1, then I would have two equations. I could figure out the trace, the determinant, eliminate one of these variables, and then use these two equations to find the other two. So if you have a 3 by 3 matrix, you have one of the eigenvalues, you can find the other two just from this property. Well, that's sort of just nice to know that there's these connections between these different things. It might also be that the the determinant of the matrix is some volume. So if it's a certain volume, if the determinant is 0, that means one of the eigenvalues would be 0. And if it wasn't 0, then the volume would be the product of the eigenvalues. So it's just a curious if you connect everything up. Okay. Powers of matrices. That's what we're doing here. And then do some nice examples. For example, if you start from the matrix A here, you find that A to the n has this weird form here that's got the same kind of pattern. And you can go through and do this calculation, Wx maxima. So here are two possible examples. Here's M, you could practice with this and this. And so, but that's what we need for the applications. Okay, so this is sort of like the